Okay, I think I will begin now and would like to introduce our speaker. So I am delighted to have Henry Towsner from the University of Pennsylvania to deliver this second talk in this seminar series. The subject of the talk is not only intriguing, but also very important because it obviously concerns one of the central open questions in proof theory. So I'm quite intrigued and delighted that Henry Towsner is delivering this talk. A few words maybe about, so everyone, specialists know Henry for his work in constructive mathematics and in reverse mathematics and recursion theory, randomness. So his range of interest is in fact quite broad. Yeah, so Henry, please begin.
All right, Lev, thank you so much for having me here, and thank you all for being here. I keep wanting to say good morning, but it's only a morning for a few of us. So whenever it is, thank you for being here. So yeah, I do want to talk about ordinal analysis for second order arithmetic. I tried to make a guess at the right level of proof theoretic background to assume, but in particular, if I assume too much, please don't hesitate to interrupt and ask me to actually explain things clearly. So this is a Schutte style ordinal analysis, and I think it's useful just orient in what the structure of that is, which is we're going to start with a theory, and in this talk, that's always going to be in the language of second order arithmetic. And the first step is to write down an infinitary sequent calculus, a sequent calculus with infinitely branching rules, and take proofs in the original theory and embed them in this new infinitary theory. And then we prove cut-elimination in this new theory. And the hope often, and in the proofs I'm going to talk about, the second step, that embedding part, is actually the hard part, and usually this pays for itself by making the third step, the actual cut-elimination proof, much simpler. Ordinals enter into this story very naturally because when you're talking about infinitely branching proofs, they need to be well-founded. They have ordinal heights. Well, they don't need to be well-founded, as we'll discuss, but a priori you would expect them to be well-founded. They have heights given by ordinal bounds, and then the ordinal analysis part of ordinal analysis comes from looking at the ordinal heights of the proofs that show up in this cut-elimination process. So everything I want to talk about is kind of motivated by and starts with an analysis of the theory that's called pi11 CA0 minus. That's parameter-free pi11 comprehension. It is one of the sort of simplest impredicative theories, one of the first theories where new issues come into play. Formally, it means essentially there is one instance of pi11 comprehension. And I guess I'll say slightly more precisely what that means in terms of the rules. So I'm, throughout this talk, going to ignore, these are all built on first order arithmetic. I'm going to ignore the first order parts of these theories because everything that happens there is well known and very standard. The significant fact about pi11 CA0 minus is that it's a second order theory. It has set quantifiers and it has rules for introducing set quantifiers. The for all introduction rule is standard. It's if you prove phi of y where y is sufficiently fresh, then you can prove for all x phi of x. And the interesting thing is happening over on the exists introduction side. So often comprehension is written as an axiom, but I like to write it as a rule to really emphasize that it's the relevant form of existence introduction for us. So if you prove gamma phi of psi, and what I mean by that is phi has a free variable x, you go through the formula and you replace the formula n is in x with psi of n. So implicitly here, psi has a free variable as well. And so when you replace x with psi, you replace the free variable in psi with whatever n you're asking about being in x. So if you can prove gamma phi of psi, where psi is parameter-free pi11, so psi has the form for all x psi prime of x with psi prime arithmetic, and with no further set variables, no set quantifiers and also no set variables. That's the parameter-free part. So under those conditions, you can conclude there exists an x phi of x. And now is a good moment to point out, as the notation here suggests, it's typical here to work in a Tate calculus, a one-sided sequent calculus. So this is like the right-hand side of a more conventional sequent. A sequent is just a finite set of formulas. We interpret them disjunctively, so this really means if we've proven that either gamma or phi of psi, then we've also proven either gamma or exists in x phi of x. And relatedly, because it's classical, we push all the negations inside. So you'll only see me write negations of atomic formulas, and if you have a negation of anything else, you just use the De Morgan rules to push it all the way. All right. So the obvious proof to cut elimination fails. So the simplest thing you could try to do is you take a cut between an exists formula and a for all formula, and let's say that they're immediately introduced, the cut is immediately after the introduction rules for simplicity. So what you might hope to do is you say, well, I have the psi over on the left. I substitute the psi for the free variable y on the right, and I get a proof of gamma phi of psi from the left. This proof on the right becomes a proof of delta not phi of psi, and now I have a cut between phi of psi and not phi of psi. Nothing is formally wrong with just this replacement. Like everything here is correct. You could take a cut over pi11 formula and replace it like that, but psi is pi11 itself, or at least it could be, which means phi of psi is typically more complicated than psi. For example, psi could literally be the formula for all x not phi of x. So we've replaced this cut with a cut over a more complicated formula that represents exactly the same cut. So this process, if you tried to carry it out, you would just end up in cycles, eliminating cuts and replacing them eventually with the same cut again, and you wouldn't make any progress. Exactly the same phenomenon for the same reason shows up in ordinal analysis of like fixed point logics, things with mu operators, and the issues look very similar. So the solution I want to talk about is due to Buchholz. So there are a number of solutions to this. Buchholz came up with an ordinal analysis or with an approach to this theory, I think sometime in the late 70s. And Buchholz's approach goes like this. So we're actually going to need two theories. The first, which I'll call T infinity 0, this is an infinitary system for first order arithmetic. So it's essentially infinitary Peano arithmetic. It has the little omega rule branching over the natural numbers, that this isn't so important. And it also has the second order for all introduction rule. So importantly, this is a good theory for proving pi11 sentences, but it has no introduction rule for second order exists. So then, of course, we extend to the full theory, T infinity, which adds a second order existence rule. And Buchholz calls this the capital omega rule, by analogy to the first order lowercase omega rule. And this rule takes a little bit of explaining. So it's an introduction rule for a second order exists quantifier. So we're going to prove either gamma, either some side formulas hold, or there is an x so that phi of x holds. There are infinitely many branches. The branches are named by proofs. So for every T0 infinity proof, I sometimes call this the small theory. For every small cut-free proof of not phi of y, possibly with some side formulas delta, we have a branch, and in that branch we have a proof of gamma delta. So there's infinitely many branches, and they're named by proofs. That's the unusual feature here. And the sort of interesting step that I think in particular helps illustrate how this rule works is the embedding step. How do we take a comprehension rule, which is like a normal, well-behaved exists introduction rule, and replace it with one of these omega rules? So formally, we have to prove if pi11 CA0 minus proves a sequent gamma, then this new system T infinity proves it. The proof is mostly standard. We started with a finite proof. We proceed by induction step by step. And the interesting case is when the last step in this proof happens to be a comprehension rule, because then we have to replace it with a new rule. So by the inductive hypothesis, we assume we've already translated this proof of gamma phi of psi into an infinitary proof of gamma phi of psi. And now we want to apply an omega rule. So the branches of the omega rule are named by small cut-free proofs. So we say, well, what do? Take one of these cut-free proofs, Q, a proof of delta naught phi of y. I need to give a proof d infinity Q of gamma delta. And what I do is almost the steps we wanted to do before, except they'll work now. So we take this free variable y, we replace it with the formula psi, and then we apply a cut between gamma phi of psi and delta naught phi of psi, which might be a cut over a more complicated formula. And that's fine, because mostly what this rule has done is reorder the steps so that we'll do things in a non-cyclic way. So we get these proofs dq infinity for each q. They have exactly the form we need. And so the omega rule gives us a proof of gamma comma exists in x phi of x, exactly as we had hoped. This argument uses in an essential way the claim, right, that we did the substitution. We took a free variable and we replaced it with the formula psi. And that's what you expect to happen, but it plays a central role. So let me mention that explicitly. So there's a lemma. If you have a small proof of gamma of x, where x is a free variable, you can replace all the x's with psi. You do this exactly the way you expect. You just go through the whole proof. Who cares that it's infinitely branching? So you just go through step by step and you replace every x with a psi. There's an important fact about our proof system, which is rules are preserved under replacement of free variables by a formula. Right? If I have a formula, one of my rules was an OR introduction. I proved phi1 of x or phi2 of x using for OR introduction. I could just as easily prove phi1 of psi or phi2 of psi using OR introduction. And I could proceed inductively up the tree. In fact, technically, there's a rule for which this substitution doesn't hold. There's an axiom that for any atom, including the formula n is in x, we can prove n is in x or not n is in x. And when we replace that with psi, we get something that's not an axiom, but we can deduce psi of n or not psi of n. So we replace this axiom with a deduction. All right. Having done the embedding, the cut elimination step is more or less standard. We need the assumption that the conclusion is universal. The conclusion does not contain a second order exists. And given that, the cut elimination goes as follows. First, we eliminate the arithmetic cuts. And let's say we were left with cuts of this form, where you have a cut immediately below the introduction rules.
Seems to be a negation missing.
There should be a negation right here, yes. Yeah. I caught a lot of the missing negations, but yeah, I see I left one. I'll say later, technically something slightly different happens, but it's morally equivalent to this. So you're left with cuts that look more or less like this. Gamma delta is universal. And we proceed as follows. First, we do cut elimination in the left branch. Right? That is, we reduce all the cuts in the left branch. And now we say the left branch is a cut-free proof of a universal formula, of a universal sequent, which means it's actually not just a proof in T infinity, it's a proof in T infinity 0. There can't be further omega rules, because an omega rule would introduce an exist statement, which without any cuts, we have no way to get rid of. So the left side is actually in T infinity 0, which means there is a branch of this omega rule that exactly corresponds to this thing here, and it is already a proof of gamma delta, because that's exactly what the omega rule was defined to do. And then inductively, that is also a proof of a universal sequent, so we have also done cut elimination on the right-hand side. And that is the final cut-free proof of gamma delta that we wish to have. Okay. A thing you might notice is I actually didn't make any direct reference to why this only works for pi11 formulas. Somewhere in here, we must have used that in an essential way, but actually the use is a little bit subtle. So it's actually in that substitution step. So I mentioned in passing that rules are preserved under substitution of free variables by formulas, but that's not true for the omega rule. The reason is this. I like to think of the omega rule as really encoding the graph of a function. Right? The omega rule has a set of input-output pairs where the inputs are small proofs, and the output is the small proofs of not phi of x, and the output is the corresponding proof of gamma. So if we tried to extend this to, say, pi12 comprehension, the step you would get to is that you would have an omega rule introducing an existence formula with a free variable, and you would like to substitute y with a free variable. So you are given a function whose domain is proofs of the form delta not phi of xy, and you need to replace it with a function whose domain is proofs of delta not phi of x psi. And it's not at all clear how to do that. This sort of arrow-chasing thing you'd like to do is replace psi with y, but you can't do that. You can't backwards substitute formulas for free variables because, for example, psi might also appear in delta in an essential way. So the backward substitution doesn't work. And this method sort of gets stuck here. There's ways to extend it to, say, full pi11 comprehension and a bit beyond that, but they very crucially involve never trying to do a substitution inside an omega. All right, so that is the problem, as I understand it, is how do you deal with how do you extend the method of the omega rule where you actually want to substitute in the omega rule? I guess for the rest of the talk, I want to talk about the solution. So the motivation comes from the following idea. So, right, ordinal analysis is constructive. What are we doing with infinitely branching rules in constructive theories? And the answer, which you can't always, is actually a little hard to find written down. Like, people often don't say this so explicitly, but when you're doing ordinal analysis, you do know that you're only using these infinitely branching things in ways that are really could be encoded by computable functions. So when you have a little omega rule that branches over the natural numbers, in the back of your mind, there's always this idea, well, it could have been a computable function which takes n as an input and outputs a code for a proof of phi of n. And similarly, this capital omega rule, right? It could be all the functions we use are actually computable. You could take a code for a proof as an input and output a code for a proof. But actually, the functions in the omega rule are even nicer than that. There's this observation due to Mintz that they're actually continuous in a certain way. And the thing I want to do is exploit that continuity. So here's a story. We often think about proofs as being like defined inductively from axioms and built up. But for this talk, it's going to be useful to think about proofs sort of co-inductively, built from the bottom up, in a way that encompasses ill-founded things as well as well-founded proofs. So here's how I like to think about proofs for this. A proof is a function, maybe a computable function, and the inputs to this function are positions, and a position here is a path from the root, starting at the conclusion, up to somewhere in the proof. And at a position, d of that position is the rule that occurs at that position. So the idea is the empty position, the conclusion, is always a position in a proof. And then if you know what the rule is, you know what the premises of that rule are, so you know that you know some other positions that are in the domain. If you find out that the last rule is a cut, now you know there's a left branch and a right branch. So you know that D of the left branch tells you the bottommost rule in the left branch, and so on. And so we can think of proofs this way. And of course, to be a genuine proof rather than a pre-proof or proof tree, it needs to be well-founded. It's useful to think of these as a dialogue. So I imagine that you have a proof of something and you're trying to convince me of it. And we could have a dialogue where I say, how did you get that? What is your final step? That is, what is D of the empty sequence? And you tell me a rule. You tell me, oh, you tell me you've proven a contradiction from second order arithmetic or whatever. And I say, oh, that's very surprising. How did you do that? What was the last step? And you say, oh, well, I proved phi and I also proved not phi. And I think about that for a minute. I go, tell me about not phi. How did you prove not phi? And so you tell me, your last step in the proof of not phi, and we can keep going this way. And of course, you need to not go forever, but we could learn about the proof through this dialogue. And I want to emphasize in this dialogue, when you talk, you say rules. And when I ask questions, I name premises of rules. I say, which branch do we go up? Okay. So now, instead of supposing that you have a proof, imagine that you have a function on proofs, and I have the proof. For example, this substitution function. I have a proof of phi of x, and then you say, oh, well, if you know how to prove phi of x, I can prove phi of psi. And we have this dialogue, and I say, well, how did you prove phi of psi? And you now have a new move available, which is you can, instead of telling me about your proof, you could ask me a question. You could say, well, how did you prove phi of x? And then I say, oh, I used and introduction to prove phi1 of x and phi2 of x. And then, of course, you say, oh, well, then I used and introduction to prove phi1 of c and phi2 of c. And then I say, oh, how did you prove phi1 of c? You say, well, how did you prove phi1 of x? And we go back and forth like this. But this is actually the same. This is just a dialogue. You say things and I say things. The things you say are rules and the things I say are premises. So we could think of a function on proofs as just being another thing we can prove. And you have a new rule in the proof system, which corresponds to the step, no, you tell me how the input was proven. And the branches of that are the answers I could give. The branches to that are the rules I could have used in my proof of phi of x. So this is the core idea, that we're going to be able to extend our proof system so that functions on proofs are just things we can prove. This is where the name of the talk comes from, right? Proofs that modify proofs. So what we're going to do is introduce a new kind of formula, which I think the preprint online uses a different notation for this, and I eventually came up with a notation I like more, which is this bracket sigma. So the formula bracket sigma epsilon is supposed to represent that there is an input proof. We are proving a function. It has an input. The input is a proof of sigma. So I think of the box as being like a hole that you would plug a proof of sigma into. And that epsilon is a position. So this says that we're going to look at the proof at position epsilon. So the sorts of things we expect to be able to prove are things like the identity function, bracket phi empty position phi. Right? This is supposed to be the sequent that says there's a function that takes a proof of phi and gives a proof of phi. And inversion, right? The thing that says if you have a proof of phi and psi, then you have a proof of phi. We should be able to prove that sequent. And most relevantly for this talk, there should be a proof of bracket phi of x, comma, phi of psi. There's a function that takes a proof of phi of x and gives a proof of phi of psi, and it should be provable in this way. The crucial rule, I call the read rule, because I think of it as like a computer program reading from its input. And this is the rule that is exactly that step where the person who has proven the function asks, tell me about your proof. Tell me about the input at position epsilon. And it is an infinitely branching rule, and it branches over the rules that could appear in the input proof. So whenever you define a theory that has read rules, you have to say what theory are my functions coming from? What theory are the inputs coming from? And the read rule then branches over that theory. So, for example, it might branch over that small theory, t infinity 0. I'm not really going to justify why it looks exactly like this, other than when you sort of fiddle with how end sequence work, this really is what works out. A thing I should mention is these ... dots. They stand for the fact that there are some ordinary formulas in the conclusion and premises of the read rules. They have to do with what's going on in epsilon and what the conclusion of the rule are in this branch is. And rather than write out all the notation to tell you what they are, I will tell you in like 2 slides what is the theorem you would prove to justify that you've defined the read rule correctly.
So maybe may I ask at this point, so to better understand. So if, this all techniques, so you essentially define these constructive operators on proofs, and proofs are these branching structures, so to say, defined on functions over sequences. And so you define it in this dialogue way. So the condition of well-foundedness does not occur. So at this point, so you de facto you define these continuous operations over these
So yeah, so just like in a proof of, so when you think about ordinary, forget about proofs of functions. When you think about ordinary proofs this way, you get pre-proofs, proof trees, and you have to add a well-foundedness condition. And similarly, if we're dealing with functions, we are going to need a well-foundedness condition that I will say more about.
But at which stage does it occur? At the level of definition, or at the level of verifying that something is indeed a proof or something like this? So
so usually what so really what you do is you define I call them proof trees. I think in the literature other people like to call them pre-proofs. And so you say these functions, these potentially ill-founded trees, they are pre-proofs. And then you have to say a genuine proof. The definition of a genuine proof is that additionally it satisfies a well-foundedness condition.
And then you expect that your operations that you have already defined, they transform proofs into proofs. They preserve the property of being a proof. Something.
Yes.
Like okay. Yeah.
Yeah, and I think I will say more that might also help clarify this. So I just wanted to illustrate very briefly what one of these might look like before I get there. So the simplest non-constant function would be the identity function. Right, so say I want to prove, given a proof of phi and psi, I have a proof of phi and psi. Right, so I could, well, the introduction rule for bracket formulas is the read rule. So I give a read rule. It has branches corresponding to all the rules that could appear in the input. So for example, there's a branch corresponding to the and introduction rule that introduces phi and psi. A thing I should say, because I know this has been sometimes confusing. When I say that it branches over rules, I don't mean it has a branch for any and introduction. When I say a rule, I really mean a full specification of how it acts on formulas. So there's a branch for and introduction specifically introducing phi and psi, and introduction for a different pair of formulas would be a different branch. But so one of the branches is we introduce the main formula that's interesting here, and the definition of the read rule says that we have a branch which should have a proof that we look at the left branch, which has a phi in it. We look at the right branch. The left branch concludes phi. The right branch concludes psi. And we should prove phi and psi. And of course, we copy the rule over. So if we had an and introduction, we should place an and introduction. And then we now have a proof of, from phi, we can prove phi. From psi, we can prove psi. And we would continue inductively or co-inductively in some sort of iterative fashion, building. There would be more read rules above these. There's also, because our proofs are allowed to have side formulas, it could also be that we look at the bottom rule and it's a proof of theta or rho, where theta or rho are some other formulas that didn't have obvious relationship to this. And again, we should copy over the rule. So if this was a proof of theta or rho from a proof of rho, well, we should copy that over. We pick up a rho. We are allowed to prove rho now because we know that there's going to be an or introduction dealing with it below. And again, we would place another read rule above this. And exactly what I was planning to say here, which is now more relevant, thanks to Lev's question, is to point out that we haven't made any progress towards analyzing phi and psi. So we would place a read rule above this, and it could have another branch with an irrelevant or introduction, which has a read rule above it with another branch with an irrelevant or introduction. And there's going to be an infinite branch here, where we just keep looking at the input proof, and the input proof is actually ill-founded and never answers anything. And that will lead to an infinite branch of our proof of bracket phi and psi, comma phi and psi. Okay, so the crucial fact, like when you start setting up this machinery with bracket formulas and read rules, the crucial thing you need to say you've done anything useful is that these proofs of functions need to give you actual functions. So the theorem should say, theorem does say, if f, and I'm writing f, it looks like a function, but it's a proof. It's a proof of bracket sigma comma gamma. So if you give me a proof of this function, and you also give me a proof d of sigma comma delta, then there is a natural way to turn that into a proof bar f of d, applying the function f to d. And what you do is you just take the proof of f and you just copy it over, you read up through it step by step, except when you encounter a read rule, you delete the read rule, and instead you choose a branch. Which branch? Well, of course, you look at D to tell you which branch is supposed to go there. And in that way, you sort of pick a particular branch out of F that corresponds to applying F to D. And the lemma you need is that bar F of D is a proof of gamma delta. Right? When I say the read rule has these like extra formulas in it, that's the fact that you would want it to have, that that it acts on formulas in the right way. And you can, there's some setup of the theories so that you can include restrictions like this works, but it only works if D is a proof of a universal sequent. It only works when D has certain restrictions, and the general framework can make sense of this sort of restriction. Okay, so just to bring this part of the talk back together, we can reconstruct Buchholz's approach to cut-elimination for pi11 CA0 minus, which is really just restating what Buchholz did in slightly different language. So the small theory, the theory T infinity 0, is unchanged. But then we have, instead of having Buchholz Omega-rule, we're going to use these functions. So we add read rules. They branch over T0 infinity. So when I say it branches over all the rules it branches over are the rules of T0 infinity. And then we add two rules that let us use bracketed formulas to conclude ordinary sequence. And one of them is the omega flat rule. So I call it omega flat. I think of it as taking Buchholz's omega rule and, well, flattening it, because instead of writing out the graph of a function, we have the algorithm for the function, right? The omega flat rule says, I have an algorithm for this function that deletes not phi of y above here using read rules. And it's a single premise rule that says this. And this was true in Buchholz's version as well. There's this auxiliary version that is a fusion of the omega rule and a cut rule, which I've been calling cut omega. Sometimes they're called like omega and tilde omega, and I can never remember which is which, so I just gave up and I called this cut omega because it's a cut plus an omega. And then you could repeat Buchholz's proof without substantive changes. There's an embedding theorem. Right, so the important step in the embedding theorem is proving the substitution function, because once you can prove the substitution function, you can then use an omega flat rule to prove comprehension. And the modified version of this collapsing step, this step where we eliminate cuts now over bracketed formulas. And the idea, once again, is we eliminate all the other cuts first. We have a proof of a universal sequence. And first, we eliminate all the cut omega rules in D, so that, and since the conclusion is universal, D is now a small proof, a proof in the system T infinity 0. And we call that D of D. And then we apply the function. So all D of D is now exactly in the domain of this function. So we can apply the function. We get a proof of gamma delta. It might have cut omegas in it. So we collapse those as well to get a completely cut-free proof, cut-free and cut omega free proof of gamma delta. This step should raise some concerns about the nature of the inductive hypothesis, because bracket F of D is not, it's not a premise sequence, something. So you have to set this up a little carefully to make sure that well, it's not quite, it's really a co-inductive step, but you have to make sure this is well defined, and you have to worry a bit about well-foundedness of the things you get out to finish that.
Okay, so if you compare this version of Buchholz theorem to the original one, so what plays the role of what? So your read rules and your cut rules, so what do? They essentially encode some partial cut elimination algorithms or something like that in terms of the original derivations.
Yeah.
Mm-hmm. So this is a little bit similar in spirit, in the spirit of the paper where Buchholz explained the Gensen steps of cut elimination in terms of omega cut elimination.
It is. There is a direct route from that paper to this. Yes, that was.
Okay. Yeah. I see. Mm-hmm.
Yeah. So yeah, Buchholz wrote down something that was in some ways very, very close to this. Mm-hmm. Yeah, where he did exactly, where he did something similar. I think he did not break it down. He had like steps corresponding to cut reduction, and hadn't quite broken it down to this rule by rule transformation aspect. But yeah. Okay. So why does this? So of course the point of this is not to redo something that Buchholz did, 45 years ago now. The point of this is to push this forward. So why does this help? So the Omega rule is justifying, any rule is giving us a story. How do we justify a second order exist statement? The Omega rule says, well, we have this graph of this function recording how proofs get transformed. The Omega flat rule says, actually, we have this algorithm. And the important fact is algorithms are, they typically are more robust under certain kinds of changes, because you can take the statement, take this algorithm from that domain and apply it to a new domain, by which I mean just do what you did over there, do the same steps here. And that's sometimes a sensible thing to do. And fortunately for us, it's sensible for us. So let me try to illustrate this by kind of diving in on what is the hard step if you wanted to extend this to Pi12CA. Well, the obstacle, if you just took what Buchholz had done and you just started trying to do it for Pi12CA, you would bog down on the embedding step. So you have this step where you have a finite proof of now you need to introduce a sigma 1,2 statement, exists X for all Y, and you want to embed it as something like this. And in particular, you want to give this proof of the substitution function. You want to prove, given a proof of exists a y not phi of xy, I have a proof of exists a y not phi of psi y. And to do that, we need to write down the substitution function. which means I need to take a proof of exists of y not phi of xy. I need to produce a proof of exists of y not phi of psi y. And presumably at some key point, I introduce this second order exists using an omega flat rule because that's what we have available. And I introduce the corresponding bracketed formula using a read rule. And now I need to produce a new read rule. And the point here is I can't just copy over the old read rule because the new read rule, right, I've changed the end sequent. I have correspondingly changed, in fact, the theory over which this read rule needs to branch. So it's now really a new read rule. I can't just copy over the old one. So here's what I'm going to do. The branches of a read rule are given by the rules of the theory that the input is coming from. So I'm going to try to construct the branches of my new read rule. So I look at my new read rule, and in the input theory, there's some rule R0. Say that R0 is, say that phi is a conjunction, and R0 is the corresponding and introduction. Well, if I can prove phi1 of psi and phi2 of psi, right, there's a corresponding and rule for phi1 of x and phi2 of x. Right? There's a rule in the old theory that is analogous to the new theory under that circumstance. And so then what I do is I identify the corresponding rule in the old theory, which I'm calling here R0 left arrow, right? The backwards version of R0, the version of R0 in the old setting. And there's a corresponding branch, and there's some, and here I'm getting into the gory details of the read rule that you have to look at to justify this. There's the necessary relationship between the corresponding branch of the old system and the corresponding branch of the new system. And so I can use the branch above R0 left arrow to guide the development of the branch above R0. It could also be, right, there are many rules here. There's also some rule R1, and R1 is actually doing something totally irrelevant to phi that furthermore doesn't correspond to anything in the old system. Right? Psi could be very complicated. So a proof of phi psi of y could suddenly be much more complicated than a proof of phi of xy, and it could involve new rules. So, but what I'm promised is if R1 is doing something sort of new and complicated, it's not interfering with phi. So a crucial fact here, right? In most sequent calculi, each formula has often like a single introduction rule that kind of governs how that formula behaves. So a crucial fact that gets used here is when we have new rules, they only introduce new formulas. They don't give new introductions of old formulas. So if R1 is a new rule, we're guaranteed that it's not going to interfere with in particular with phi. So then again, we look for a different R1 back arrow. For example, our theory is going to include the repetition rule. The repetition rule is a rule that doesn't do anything. It proves gamma from gamma. It's like a placeholder rule. So one thing we can do is where the new proof R1 is doing something new and complicated, we just tell the old proof it's irrelevant. Let's just go with the branch where nothing happens because nothing has happened in the part of the proof we care about. Okay, so this is obviously the sort of touchy technical part of the proof where you actually have to verify that your proof systems satisfy this. But it's actually mostly just a little bit of combinatorics and tracing through how the formulas work. The important fact is to notice that we're not just copying branches over. We actually have to do this somewhat complicated rearranging of branches to translate the old read rule to the new rule, which I should emphasize is totally new. When you substitute in an and rule, the left branch becomes the left branch, the right branch becomes the right branch. That's not what happens here. Okay. Right, and it's really worth emphasizing. We don't need the new read rule even branch over the same theory. We can actually change the domain. We can do a process I call lifting, where you make the domain larger. You just need this backwards map that says for every new rule, there's a corresponding old rule that does the same work on bracket phi. I haven't said anything about well-foundedness, which, I mean, I guess you can see from the slide titles. Obviously, I owe you that. But that said, that technical bit is the work, and then you do get a new ordinal analysis of pi12 comprehension. And this is the thing that was sort of miraculous that I did not expect when I started doing this, that because functions are now just, so if you did this for just pi12 CA, maybe I should say, you could use this new read rule machinery to deal with pi11 comprehensions, and then you could use the Buchholz Omega-rule for pi12 comprehensions. But you don't need to. You could just go ahead and use the new stuff for the pi12 comprehensions as well. And the point is, because functions on proofs are just proofs, this process just sort of swallows itself up. Functions on proofs are just proofs, so then functions on proofs, which are what you would want to do to deal with pi13 comprehension, they're just functions on proofs, which are just proofs. And so you can just iterate this all the way through full second order arithmetic, which is obviously a lot to say as a, well, you know, one little slide here, but okay, so maybe I should put quotes around straightforwardly. I mean, it's obviously a lot of technical work, but the core idea, it really is nothing more than what I've said. Okay. So having said that,
when you're speaking about ordinal analysis here, are you actually able to extract ordinal bounds from this method?
Yes, with more difficulty than I'd initially hoped, but yes. And that is indeed what I wanted to talk about for the rest of the talk. Okay. So first of all, I said we're talking about ill-founded proofs now. So these proofs of functions are unambiguously and unavoidably ill-founded. So how do you get ordinals out of ill-founded proofs? So there's now a substantive literature on ill-founded and cyclic proofs. And what happens in all these settings is you have this general idea. You could have like something that looks like a proof. It's a tree, but it's ill-founded and it's badly behaved. It's just loops, with weakening over and over and over again and doesn't do anything. So what you want is to restrict to a class of proofs that's where the infinite branches satisfy some condition. And most commonly, that's expressed as the branch having what's called a trace, which means there's an infinite subsequence satisfying some property that guarantees that you're making progress in some way along the branch. In a cyclic proof of an induction, you should like descend in the induction infinitely often, or something like that. And what we need to get an ordinal analysis is a quantitative version of that. So here's how I approach this quantitatively. So when we have one of these, so a preproof, and here I really explicitly mean it's one of these functions from positions to rules with no promises about well-foundedness, and therefore it might really not be a good proof. An ordinal assignment is going to be a function which assigns to each position an ordinal bound so that the ordinal bounds are decreasing. But in a potentially ill-founded proof, those bounds are allowed to include variables. And so in my context, what we require is if the variables are named by bracket formulas, and you're only allowed to include the variable v bracket sigma in a proof of bracket sigma. Right? So if you're proving an ordinary sequent, you should have ordinary ordinals. But when you're in the middle of one of these proofs and you have a proof of a function, you're allowed to have these variables. And of course, the variable stands for the ordinal height of the input proof.
Right. And so when you are dealing with individual proofs, then you have sort of individual ordinals. But if you are dealing with proofs which are actually operators or operators on proof, then you presumably have these ordinal functions.
Yeah.
And then you will obtain this kind of thing, right?
Exactly.
Mm-hmm.
And the definition you want is that V sigma epsilon iota is smaller than V sigma epsilon. Because remember, epsilon is the position in the input proof. So epsilon iota is a higher position in the input proof. So if we were given as an input a well-behaved proof, the height at epsilon iota would be smaller than the height at epsilon. And so in particular, if you assign ordinal terms with variables in this way, well, it might be ill-founded because these variables really could have infinite sequences, but your promise that every infinite sequence really corresponds to infinite reading an infinite branch of the input. The only way to get an infinite descending sequence of rules is when you're really like reading over and over again on an infinite path.
Mm-hmm.
And what that is really going to mean is a genuine proof of a function should have the property that it maps well-founded proofs to well-founded proofs, right? So the setup, because of the continuity, you have to be talking about functions on pre-proofs. So you map pre-proofs to pre-proofs, and additionally, you should preserve well-foundedness. And that's the mark of a genuine function on proofs. The crucial fact that implements this is that function application is exactly substitution of ordinals for these variables. So if I have a function f and a proof d, and they both have ordinal assignments, OF, right? The ordinal of f is some function beta of v, the ordinal of d is alpha, then when I apply f to d, I should get an ordinal assignment assigning beta of alpha to the result of the function.
So, so some people recently revived this idea of using delators. So there are. So is it more or less a delator that you are dealing with here? So that's
Yes.
Okay. Mm-hmm.
Yeah, I don't know. I don't understand dilators well enough to have really sat down to prove things along these lines. But yeah, it's at least at a pre-rigorous proof level, it's very clear. Yeah, these are dilators.
Right, because dilators are certain functions on linear ordering that should preserve well-foundedness, right? So that's
Right.
basically what you are dealing with here. So that's
Yes.
okay. Okay, so this. Mm-hmm.
Yeah, no, it matches up very nicely to yeah.
Mm-hmm.
So just to give one illustration of what these look like, right? The substitution function where you replace x with c, well, it's almost the identity, right? You basically replace every rule except where you were proving something with x, you prove something with c, except that at the axiom, you had to replace an axiom with like a short deduction. So when you go through, the ordinal bound is alpha plus v of bracket phi of x. Right? What is the ordinal bound on this? Well, it's going to preserve the height, except you have to add some fixed constant amount at the beginning. So that's I think what you would have expected given these definitions. It's how things ought to behave. Okay. So the challenge, and the next part of the talk is if you are very familiar with the notation for the Howard-Bachmann ordinal, I think this will be clear. And if you're not, the next interlude gets a little technical. But I think, well, it won't be forever. I tried to limit this to a piece of the talk. I'm breaking my promise to never talk about ordinal notations in public. So the question is, how do you, in our proof system, we have a step where we go from a proof of a function to a proof of a sequent. And proofs of functions are allowed to have variables, and proofs of sequence are very importantly not allowed to have variables. What do you do there? And the answer, just like in every ordinal analysis of pi11 CA0 minus, is you need to do something a little special. So you introduce a special symbol called capital omega. This is usually what it's called. And I'm going to think of it as like a meta variable. It is larger than any variable. But unlike the variables, it is allowed to appear in ordinary bounds. Right? So that's the first step of our solution, is we just say, okay, there is I can't put variables in a proof of an ordinary sequent, but I do get to use this special symbol. And you can think of it a little bit as a warning. Like if you see something with a bound that has an omega in it, it's like a little bit of a warning. Above here, I'm not a function, but I might use functions in my proof. Above me, there are functions. Right? I might not really be well-founded, but there are some rules about how complicated the functions above me can be. So when you write down proofs and you do cut elimination, you get bounds like capital omega plus 7, omega to the capital omega plus 7, right? You have bounds that look like ordinary ordinal notations, except they do have these capital omegas in them. And so in the literature, these are usually construed as uncountable ordinals. And then people sometimes refine that to say, well, maybe they're ordinals above the first admissible because we don't like uncountable ordinals. So there's this two-step where they're ordinals, they sit in our ordering, but omega is larger than all the countable ordinals, and things with capital omega are different from things with countable ordinals. And from this perspective, it's convenient to think of capital omega as being a little bit like a variable. And in particular, notations that include it are not ordinary countable ordinals because they're not closed. They have this variable-like thing in them. And then what we always need in our notation is what's called a collapsing function, which takes a notation involving capital omega and collapses it to an ordinary countable ordinal. And it behaves just like a variable binding operator. So if you think of omega to the capital omega plus 7 as an ordinal notation that has a free variable capital omega, theta of that ordinal would collapse it to a closed thing that does not have free variables, that is now a countable ordinal that you could use to bound an ordinary countable proof. You can derive from this, I feel very cleanly, what, I mean, if you want to write down an ordinal, you would like to extract an ordinal notation from this. Obviously, for pi11 ca0 this is very well known, has been done a number of times in the literature, but you can repeat that derivation here, and I think it comes out rather nicely. You don't get anything new. I think it's just a nice account of that story. So the key step is you have to figure out how does this collapsing function operate on ordinals? What is the comparison rule between collapsed ordinals? When is theta of alpha less than theta of beta? And the key step that controls it is a situation that looks like this. It's when you collapse the cut omega rule. So we have this situation where I have a bound gamma, and I have two branches. I have a bound alpha and a bound beta of v, because the right branch now has a function in it. And alpha and beta, because this is an ordinal assignment, they have to be smaller, and they actually have to be strictly smaller, which is a technical condition I won't get into. And recall that the way our process works is we first collapse the left-hand branch, and just by whatever collapsing means, it ought to collapse to theta of alpha. There are people here who do know this notation well, so I'm leaving out technical detail that does not change a lot, but makes everything a little bit more complicated to just work with the strict less than and not an additional piece of information. So inductively, we should, whatever theta of alpha is, it should be the height of the left branch after we collapse it. And then our process is going to substitute theta alpha into the right-hand branch, giving a deduction with height beta of theta alpha. So remember, beta has capital omegas in it. Beta is an uncountable, it's a non-closed ordinal notation. So we have to collapse that as well. So the final bound we get is theta of beta of theta of alpha. And when you go through and figure out what must the collapsing functions do, this is sort of the key inequality. You have to define the collapsing function so this inequality holds. One reason I really like this story is, so I learned, and I did not in fact know this until I was doing this and then looking into the history, that the ordinal notations around the Howard-Bachmann ordinal, I think the original version involved sort of generalizations of the Veblen phi function. And so there's this connection between collapsing functions and sort of iterated, sort of abstract fixed points of ordinal operations that sometimes gets obscured in the way people talk about these. So one thing I like is this really highlights the way that theta is some sort of fixed point operation. Because the bound we're getting is, what does theta gamma have to be? Well, it has to have the property that for every function beta, which is smaller than gamma, theta gamma is a fixed point of the function that maps v to theta of beta of v. Right, so this gives a precise way to look at, or a precise way to see why theta is this sort of abstract fixed point function. And in particular, notice that as gamma gets bigger, the class of functions under which it is closed also get bigger. And that's very explicit when you look at this in terms of these dilators, these functions on ordinals. Okay, so
so this condition essentially defines this standard
so
notation.
This is enough to define it. And then it turns out to be more work than I'd hoped it would be, but it's work to get from there to, well, how do you define theta in general so it satisfies this property? But yeah, this is sort of the governing property of the collapsing function. So nothing changes when we go to pi11 CA0. Well, okay, a lot of things change when we go to pi12 zeroize, but at a very high level, it doesn't change. You have the same situation. You want to do the same thing. Okay, the new complication is when you collapse theta alpha, it's now a proof of a sigma 1 formula, which means it has a function above it. So theta of alpha, the collapse of alpha, should actually have a free variable in it. To correspond to the fact that this second order exists statement must be introduced by an omega flat rule with read rules above it. Like, it's justified by a function, so it should have a variable corresponding to it. So when we substitute alpha into beta, alpha is a function on ordinals. So beta the thing we substitute in for beta had better be a variable that's a function. It had better be a variable of function sort. Now, gamma no longer has this variable of function sort, but it does need to bound it with a meta variable. So gamma needs a meta variable of function sort. So I've been writing this with a Greek letter xi. I just wanted to not call it omega because people are used to thinking of omega as a cardinal, and these are not cardinal-like because they're functions. They may be dilator-like, I suspect. I'm, again, not so clear on the details of how things are going to line up with dilators, but they're probably dilator-like. Right, so xi of t is some sort of meta function that bounds all these variable functions. And that same inequality holds for exactly the same reason. Right? You go through and exactly the same thing holds, except you're now substituting functions, and that introduces a new complication that I will now subject you to. Okay, so I just want to illustrate this in roughly the simplest case I could pull together to illustrate explicitly what's going to go wrong and how we're going to deal with it. So imagine that below we have the bound xi of 0 plus omega. So here xi is this function metavariable. Omega is a cardinal-like metavariable. So you could think of xi as being the bound on sigma 2 formulas, and omega is the bound on sigma 1 formulas. I'm glossing. This is a simplified setting, which should not be a surprise, but I think this will illustrate the core issue. So on the left-hand side, omega is bounding our variable. So the left-hand side is bounded by xi of 0 plus v, and the right-hand side is bounded by w of xi of 0, right? The right-hand side takes a function variable, and it's being applied to xi of 0. So the first step is I collapse the left-hand side. So I can just replace the left-hand side with a collapsed version. And I am, for reasons that will be clear, trying to be very explicit about which collapsing functions are bounding which symbols. So this is the collapse on Xi, and it's binding Xi and Xi. Nothing strange has happened yet. But then, remember, the next step is I substitute. So I take this function, theta of this thing, and I substitute it for W. And when I substitute it for W, this Xi of 0 that W is being applied to gets substituted inside a theta. So this is the new phenomenon, that we get clashes of variable names. This is why it's so useful to think of these theta functions as binding variables, because the problem that happens is exactly the familiar one of the clash of variable names. Right? This Xi that I'm substituting in, it's not the same anymore as the Xi that was collapsed. And so I need to rename things to avoid this clash. And the usual solutions to this work. You have to either rename variables or, as I found more convenient, to switch to a De Bruijn index system. So I found that this approach just sort of naturally forced us to deal with these De Bruijn indices, where when I substitute Xi in for V, well, I have to reindex things to emphasize that it's a different level of the Xi function. And so then when we collapse again, we collapse with respect to Xi. And here, right, the green theta is when I collapse beta. It's when I collapse this thing. And so it binds this Xi, but then the blue one binds this one. And so this thing with 2 collapses has to be below this thing with 1 collapse. Right, so that's, again, the same inequality. It just does take on a more complicated meaning in this setting. You can, again, ask, so how do we make sense of this? So in particular, how are we going to figure out how to compare this term? This is the theta beta of theta alpha, right, where I have substituted and then collapsed again. And so we have these nested, sort of interleaved collapses. And in particular, I have this critical sub-expression. So if you happen to know the Howard-Bachmann notation very well, you know that with the Howard-Bachmann ordinal, the ordinal for pi11 CA0 minus, the thing you do is you say that these critical sub-expressions are smaller than the bigger expression. So the first attempt you would have is you would say, well, this is a strict sub-expression. This theta Xi of alpha applied to Xi, that's a strict sub-expression of theta Xi of beta, so it should be smaller. But that cannot be. The cardinalities don't line up, because theta Xi of beta does not have free X's in it. It is on the order of omega. It's smaller than anything with a Xi. Whereas theta of alpha of Xi, this thing, it has a free Xi in it. It's much bigger. It's sort of essentially bigger than theta Xi of beta. So you can't want to just compare these as ordinals. That's just sort of nonsense. And the answer is, when you pull this critical sub-expression out, you don't get to pull the bound things. This green Xi, it's stuck. It's related to how the function is applied. It's not part of the sub-expression. So the sub-expression you pull out is not the application of this function, it's just the function. So what you get is that theta Xi of beta, it must be closed under this function. So this is a higher order closure property. Like, it's exactly the higher order version of what you had for pi1 with CA0 minus, that we now have ordinal terms that are closed under functions that sort of express directly that they're closed under functions. And then the theta operation has to express that ordinals are further closed under all the functions that are defined within them. So there's some sort of...
At this point, I think what was a little bit too fast. So
yeah.
This distinction between the Xi0 and Xi1. So,
yeah.
So you mentioned that this is the problem of clash of variables
yeah.
there. But if you don't think in terms, so So you said something like this: C1 is the result of renaming the variables or using the Brown indices or something like this. But on the level of functions or functionals, what would that correspond to? So, C0 was, let's say, function from ordinals to ordinals or something like that. So what would be C1? So is it?
Oh, I think the way I have been thinking about this is that what is forced upon you is that when you introduce this C0, this like meta variable for functions, you actually can't introduce just one of them. It is just forced on you that you have a whole hierarchy of them. So implicitly, when you build your system, you actually have not just C0, you have C0, C1, C2, etc. And so then when you go to deal with ordinal notations involving C1, making sense of them involves also these things on C0. I don't know if that's satisfactory.
Okay.
I guess let me try one more attempt. I mean, so if this answer is unsatisfactory, it is because I don't totally understand these things yet, and
yeah, but also of course it's difficult to speak about these technical elements without, I mean, on this level of generality that you are staying on. But I'm still trying to do maximum on this level without going into any more specific details, because this is not feasible.
So forget about C's for a moment. Let's just think about capital omegas. Right. So you introduce a capital omega and you think of that as like the first uncountable cardinal, or however you want to think about it. This is the moment where I wish I had a board. So you imagine the function that takes alpha to theta of omega plus alpha. Right. So this is a well-behaved, and in the context of like the ordinal analysis on pi11 CA0 minus, this is a thing you want to operate with, where alpha is a countable ordinal. So now imagine that you wanted to apply it to an uncountable ordinal. What happens when you apply it to omega? And there's actually a natural answer, which is that instead of thinking of omega as being fixedly the first uncountable ordinal, you could think of it as being the next uncountable ordinal. So when you apply it to omega, you automatically bump the collapsed omega up to the second uncountable ordinal. Right? So this is sort of this only marginally more abstract way of thinking about the theta of omega plus alpha function. And in fact, I think when you think of it as a dilator, this is in fact the natural thing that happens. That you think of this bound theta as just always being the next cardinal after the input. So that's actually exactly what's happening here, except we have these things that are more complicated than cardinals. That this notation is forcing on us, we can't just have a fixed xi. That once we've bound a xi, it's always the next bigger xi. And we can always just, in a purely syntactic way, force it to be a bigger and bigger copy of xi by substituting things with more unbound x's in them.
But you don't need any, let's say, transfinite indices of these xi. You just need first omega of them, so to say.
Correct.
Something like that. Okay.
This is not as nice as it sounds, because you have an ill-founded sequence of them, and then you have to reindex to make sure you're looking at the finite part, at the well-founded part of your notation system. So I guess that's not how you don't need transfinite things, because you don't keep track of the well-foundedness at that level. But because C0 is actually bigger than C1, and C1 is bigger than C2. So.
Okay, our time is actually, official time is up, but of course you have a conclusion to make or something like this, and then we have a discussion. All
right. So we did at least get through the technical part. Let me very quickly make say, next steps, what are some connections? Adapt this to Kripke-Plottek set theory. So these ordinal notations are, as noted, quite mysterious. They're mysterious to me. There are existing ordinal notations in the literature that are, to be fair, also a bit mysterious, but I'm really optimistic that lining these up will be a lot of technical work, but might really be rewarding. In particular, my approach, you can sort of see some like reflection-like properties happening. Rathjen's ordinal notations involve a very explicit scheme of iterated reflection notions, and my guess is lining those up will be very clarifying about both. This is not so important, blah, blah, blah. Relatedly, okay, we have other understandings of sort of the proof theoretic strength, especially sort of around pi12 CA0, things like infinite time Turing machines, feedback Turing machines. Again, I think we'll get a lot of clarity about all of this by lining these all up, and especially maybe some insight into how to extend these notions past pi12 and pi13 CA0 through full second order arithmetic. Descriptive set theory. Yeah, it turns out the ordinal analysis here, it seems to have to do with the behavior of point classes in L omega 1 CK. And there's a theorem missing that would justify that is always the case, or why that's the case, or what it means. I'd really like to know that. Let me maybe just mention, especially given some of the people here. So ill-founded and circular proofs, there's been a growing literature on these. They need well-foundedness conditions, and as I don't want to claim this is true of all of them because I've not looked exhaustively through the literature, but they're certainly almost all pi12 properties. They say for every infinite branch, there's an infinite subsequence, which is to say, as far as I know, they are equivalent to saying that sort of infinite paths preserve well-foundedness when you view them as functions in the right way. And this means they're sort of at the proof theoretic complexity of pi11 CA0 minus. And this suggests there's a lot more to explore there, because there are these higher order preservations where you preserve not well-foundedness, but you preserve the property of preserving well-foundedness and things like this. And there's this machinery for doing a quantitative version of these trace conditions. And I think there are places where I'm certain these will have applications elsewhere in the literature, and for things like proof systems of fixed points and so on, where the right kind of bounds are not just trace conditions, but these higher order conditions. And I'm over time, so I should stop.
Okay, thank you very much.